The applications and protocols that we've seen so far were mostly based on the client-server architecture, in which there was one dedicated server which was on 24/7 with a publicly known IP address, and it would provide services to randomly activated clients. However, with an increasing share of peer-to-peer protocols on the internet, it becomes very important to understand the scalability aspects of peer-to-peer, which have given it so much of success. Therefore, in this module, we should start with an understanding of how peer-to-peer operation takes place. We'll assume a simple file distribution problem that we have seen earlier though, and we'll see how peer-to-peer addresses it vis-a-vis client-server architecture. And we'd quantitatively look at an expression for gauging peer-to-peer performance. So peer-to-peer protocol actually works with no always-on server. Basically, a client also comes with its services. So when a client joins a peer-to-peer network, it becomes an arbitrary end system that provides its own suite of services. So peer-to-peer topologies are intermittently connected with links emerging and breaking down. This process is also known as churning. The IP addresses of these peers are not well known, and whenever they come and join the peer network, their IP addresses start getting known for as long as they're part of the peer network. The file distribution problem is a simple assumed problem in which there is a server that hosts a file and there are various clients distributed all over the internet. The eventual goal is to make sure that each of these clients gets a copy of the file from the file server. The expression given before you with the client-server architecture distribution time has already been addressed. That is, given that we have an uplink speed of the server and downlink speed of the client with the minimum download speed given by dmin for n clients, the expression for client-server architecture distribution time is given by the maximum of the n times the file size divided by the uplink speed, or the file size itself, which is downloaded by the clients from the server. The new expression that appears before you for the distribution time for a peer-to-peer network is worthwhile consideration here. We'll go deeper into it in the next slide. However, the point to be noted here is the relationship between the two graphs for client-server and peer-to-peer with an increasing number of users. Here we see that when the number of users increase, at the very start, the peer-to-peer architecture and client-server architecture behave almost similar. But as the number of users increase, the overall load on the server, the channel access, the communication channel access delay, and the overall contention that takes place, client-server architecture keeps on increasing a linear, if not supralinear load on the overall network. But the peer-to-peer architecture starts getting flattened in this graph, showing that as the number of users grow, the distribution time, which is shown here on the y-axis, does not grow linearly, rather it becomes sublinear. Now, if we get back to the performance expression to determine the scalability, we would like to know if the distribution time in peer-to-peer is more bounded and limited as compared to the client-server architecture. Here, in this expression, we see a new term, that is NF divided by the uplink speed of the server and the uplink speed of all the users. Because now in a peer-to-peer network, each peer as a user is also acting as a server. So we observe that the upload capacity of the system has tremendously increased because now the upload rate of the server is now added with the upload rate of each of the individual peers. Therefore, the overall expression for the file distribution time in peer-to-peer is significantly reduced.